Welcome to the Explainer. I am going to be your flight instructor today, and you're my student pilot. We're about to embark on your very first comprehensive ground school lesson. Flying an aircraft is just this incredible mashup of aerodynamics, mechanical engineering, and pure pilot technique. Now, obviously, nobody becomes a pilot just by listening to an explainer that takes a certified instructor and hours of real practice. But today, we're going to give you the rock-solid foundational knowledge of exactly how human beings take to the skies. Let's get started. Here is our flight plan for today. We're looking at the 4 forces of flight, aircraft systems and avionics, pre-flight checks and takeoff, maneuvers and stall recovery, and finally, weather, descent, and landing. All right, part 1, the 4 forces of flight, the classroom physics. So to really understand flight, we have to understand how lift is actually generated. Lift comes primarily from the wing, which engineers call an airfoil. The specific shape of that wing is literally everything. It's a massive breakthrough that the Wright brothers famously perfected way back in their early wind tunnels. It works off Bernoulli's principle, which basically says that faster airflow over the curved upper surface of the wing creates lower pressure. So that higher pressure underneath, it physically pushes the wing upward. But hey, that's only half the story. You also have Newton's third law of equal and opposite reactions. The wing actually deflects air downward. We call that downwash, which produces an equal and opposite upward reaction. It's a combination of pulling and pushing the aircraft right up into the air. Now, a completely crucial concept here is the angle of attack, or AOA. This is simply the angle between the wing's chord line and the oncoming airflow. And, as the pilot, you control this. If you increase your angle of attack, you increase your lift. But listen up. Because here is your very first critical warning as a student pilot. If you push that angle too far, usually past 15 to 18 degrees for most wings, the airflow completely separates from the top of the wing. This causes what's known as a stall, and your lift drops dramatically. So, the whole trick is balancing the 4 fundamental forces acting on the airplane at all times. First, you've got lift pushing you upward. Then you have weight, or gravity, pulling you downward based on the mass of the aircraft. You've got thrust, which is the forward force from your engines or propellers. And finally, drag, the backward resistance you get from pushing through the air itself. For steady level flight, it has to be a perfect equilibrium. Lift absolutely must equal weight, and thrust must equal drag. Okay, moving to section 2, aircraft systems and avionics. Inside the machine, let's head over to the hangar. So what's actually propelling us forward? Well, propulsion systems vary wildly depending on the plane. If you're in a small training plane, you're mostly dealing with piston engines and propellers. These basically take chemical energy and turn it into mechanical rotation to give you thrust. But look at modern airliners. They use turbofan and turbojet engines. These jet turbine systems use high bypass fans to get just incredible efficiency when they're flying high and fast. But honestly, in both cases, the core engineering goal is identical. The engines have to overcome drag efficiently, no matter what altitude you're flying at. Of course, an engine needs a brain, right? And unless you want to get hopelessly lost, that brings us to avionics. Modern planes use what we call glass cockpits, which swap out those old mechanical dials for sleek digital screens. Your pitot-static system is totally vital here. It physically measures the outside air pressure to tell you your airspeed and your altitude. Then there's your attitude indicator, which acts as an artificial horizon to keep you oriented if you accidentally fly into a cloud. And for getting from point A to point B, you have GPS and inertial navigation baked right into the flight management systems. These computers handle complex routing and seriously assist the pilot with basic navigation. Time to put this into practice. Section 3, pre-flight checks and takeoff. From hangar to runway. Jump into the pilot's seat. Before you even think about turning the key, you have got to do your mandatory pre-flight routine. Step 1 is the walk-around inspection. You literally walk circles around the plane. You're checking the tires, visually inspecting those control surfaces, checking the fuel, and absolutely making sure those vital pitot tubes are clear of any bugs or debris. Step 2 is cockpit setup, firing up the avionics and double-checking your instruments. And step 3 is your weight and balance calculation. Remember those 4 forces we talked about? The plane's center of gravity must be perfectly positioned. If you've got too much weight too far forward or backward, it dangerously changes your stall behavior and your overall control. No cutting corners here. All right, you're cleared for takeoff. This is where the thrill really hits. You line up on the runway center line, and you push to full power, maxing out your thrust. The aircraft accelerates fast down the pavement until you hit what's called rotation speed, or VR. At that exact speed, you just gently pull back on the yoke. That increases your angle of attack, generating enough aerodynamic lift to finally beat the aircraft's weight. Once you feel that plane leave the ground, you establish a positive climb rate, tuck away your landing gear and flaps if you have them, and boom, you are officially flying. Section 4, Maneuvers and Stall Recovery, Pilot Technique. We're airborne, so let's talk about how you actually steer this thing. So aircraft move in 3 very distinct axes. Longitudinally, we roll the wings left and right using hinged surfaces on the wings called ailerons. Laterally, we pitch the nose up and down using the elevator on the tail. And vertically, we yaw the nose side to side using the rudder. But here's the trick. You almost never use just one of these at a time. Good pilot technique means executing smooth, coordinated turns. You have to bank the wings with the ailerons while simultaneously applying rudder pressure. It's a very precise combination, and it prevents this thing called adverse yaw, ensuring the airplane slices cleanly through the air instead of skinning. Now, as you climb up to your cruise altitude, the physical environment changes. Specifically, air density drops. The air literally gets thinner, which means there's less resistance. So your true airspeed, meaning how fast you are actually moving across the physical map, goes up, even if the indicated airspeed right there on your dashboard stays totally manageable. Plus, that thinner air, it totally changes how your control surfaces feel in your hands. You really have to use smooth, deliberate inputs. But what happens when things go wrong? Pilots train endlessly for emergencies. Let's say you have an engine failure mid-flight. Your very first technique is to pitch for your best glide speed, to stretch your distance as far as possible. Or what if you mess up your angle of attack and enter a stall? Stall recovery is wild because you have to fight your own human instinct. Step 1, lower the nose. Your brain screams, "I'm falling, pull up," but pulling up is exactly what caused the stall in the first place. You must immediately push the nose down to reduce the angle of attack and reattach that airflow over the wings. Step 2 is to simultaneously add power to get your thrust and airspeed back. Knowing that sequence turns a terrifying drop into a totally manageable maneuver. Almost home. Section 5, Weather, Descent, and Landing, Returning to Earth. You have to remember, flying isn't just operating a machine in a vacuum. It's environmental science in action. Weather drastically changes your performance and safety. Wind and turbulence mean you're constantly making tiny corrections to your flight path. And icing? Icing is incredibly dangerous. Ice forming on the wings actually physically changes their shape, which totally destroys that critical Bernoulli lift we learned about earlier. And if you're flying long-haul airliners, you even have to factor in massive high-altitude jet streams and literally the rotation of the Earth, the Coriolis effect, right into your flight plan. All right, we made it to our destination. Landing is really just extreme energy management. First up, we reduce power and extend the flaps. Flaps are these cool high-lift devices on the wings that increase both lift and drag, letting us fly a lot slower without stalling. We ride the glide path down at a specific calculated approach speed, which we call VREF. Then, just a few feet above the runway, we execute the flare. You gently pull back to pitch the nose up, cutting your descent rate, and you just hold it right there, hovering, until the main wheels gently kiss the pavement. Then, hit the brakes, maybe some reverse thrust, and you're down. Which brings us to our final slide, and honestly, a fascinating question about the future. Modern jets heavily use fly-by-wire technology. That means computers interpret the pilot's inputs and then electronically move the wing surfaces, which gives you amazing stability and safety protections. But as aircraft get smarter and even more highly automated, how much of flying is going to stay pure pilot technique, and how much is just going to be computer management? It's a huge engineering challenge, balancing human instinct with cutting-edge tech. Anyway, that wraps up our ground school explainer. I really hope this gave you a great feel for what it takes to take to the skies. Until next time,